saw a model reaction here. Okay, bromine being substituted. Bromine is a good leaving group, nucleophile. Displacing the leaving group. We did two different mechanisms, but only one of them is correct for this reaction. And it ended up being, this reaction is what type of mechanism? SN2. Mainly because why? SN1 involves making a certain type of intermediate. Carbocation is primary. We don't make primary carbocations unless you have to. Typically, we're going to avoid them. Now, primary carbocation that also has resonance, well, that's okay, because actually it's no longer a primary carbocation. Because if you look at the resonance structure, it's probably, or maybe they're both primary, but at least it's delocalized. A standard primary carbocation typically we avoid. Down here, when we did SN2, did we make a carbocation intermediate? No. This was just called backside attack. We've actually already looked at mechanism, because if you just, basically both of these mechanisms show two different ways to make a nucleophile to carbon bond. And I gave you that handout. Nucleophile can attack carbocation. And we know stereochemically, when we do that, we attack from both sides, right? Down here, we illustrated that the nucleophile can do what? Attack the carbon and kick off the thing. Kick off the leaving group. That was the other way, right? And we know stereochemically how that happens. Right, backside attack. Okay. We did reaction coordinate diagrams. What's the rate law for these reactions? Well, it's just how many, what molecules are involved in the rate determining step. Down here, they're both involved, right? Call that SN2. Well, the rate equation for the SN2, the rate law equation, is some type of constant, K, times the concentration of the alkyl bromide, that is the thing with the leaving group, times the concentration of the nucleophile, in this case hydroxide. Okay? SN2. They're both involved in the rate determining step. Thus, they're both included in the rate equation. Now, you can tell that from mechanism. As we looked at our mechanism, when we saw that the rate determining step, they're both involved. You can also determine that experimentally, and that's sort of discussed here. Because we know if you're doing this reaction, which is SN2, you can change the rate by changing the concentration of either one. How do you do this? You do the reaction with certain concentrations, and you determine a rate. That can be done. Then you change the concentration of one of them, and do the rate again, and see if the rate changes. Okay? It turns out that you change the concentration of either of these, and the rate will change. That tells you that you're both involved in the rate determining step. This matches SN2. What I tell you here. What's the rate equation for the other mechanism, which is SN1? Some type of constant times what? The other one is SN1, right? Just the alkyl bromide. Is the hydroxide involved in the rate determining step of the SN1? The answer is no. And since it's not involved in the rate determining step, you can change the concentration of that all you want. It ain't going to change the rate of the reaction. Make sense? It's not involved. You can double it, triple it. You ain't going to increase the rate. Amar? another handout. Okay, any questions about first page? Okay, determining mechanism by stereochemistry. We already know this, we've already talked about it. If you do this reaction, we changed it a little bit, so now we have a chiral starting material, and it's specifically just R. If you take this alkyl bromide reacted with hydroxide, by the way, here I'm showing the spectator ion, right, potassium. We see that as hydroxide, right? The hydroxide can displace the bromine, kick off the Br minus. Of course, the spectator ion sits with the Br minus now. We can do this substitution reaction. We know if you do this reaction, if you start with R here, the product will be S, and S only. S only. Thus, the reaction is an antioselective. Because we only get the S. Do we get any R here? No. Only get S. It's an antioselective. Thus, this reaction is known to give what's called complete inversion of stereochemistry. We're inverting the R configuration to the S. It's like if somehow you did something to my right hand and all of a sudden it became a left hand. It's called inverting the configuration or something. Okay? Inversion. Let's ask some questions about this. First off, this question. Is an SN1 mechanism more or less likely for this reaction compared to previous? And you may have to ask for clarification of the question, but more likely. Why do you say more likely?
We didn't want to do an SN1 reaction on the previous one because it would make a primary carbocation.
Yes.
It makes a secondary one.
But this would make a secondary carbocation if the bromine just ionized off. And yes, and secondary is better than primary. Yes, SN1 is more likely. Yes, more likely. Does that mean it's SN1? Not necessarily. All I'm saying is it's more likely. Well, number two, which mechanism, SN1 or SN2, does the stereochemical outcome support or indicate? Alex?
SN2.
SN2. Why SN2?
Because the stereochemistry reverses so fast.
Yes. Because mechanistically, what happened here? How do you get inversion? The nucleophile attacks. Now this is all on the plane of the board, but the bromine's going back, so how does the hydroxide come in? Yeah. We kick off the leaving group. All at the same time, we call that concerted. Backside attack, kick off leaving group. Concerted backside. Right? Backside only. Now you got to be careful. What does backside mean? It sounds like it's coming from behind the board. No? That's not what backside means. Backside really means opposite side. Opposite to what? Leaving group. The bromine is going back, so backside is what? It's like this. Bromine's going back away from you, right? So what is backside? It's actually over here, which is actually towards you. So don't confuse what backside means. Backside really means opposite side. We call it backside. All right? And so that's why this is here. If it was SN1, what would be the stereochemical outcome? Which involves making a carbocation. How you get carbocations? Either side. And so what would be the stereochemical outcome if you did SN1? Would it be an antioselective or would it give you a racemic product? Yes, SN1 would give a racemic product. Because you get attacked from both sides, and you would get some product with the OH forward, some product with the OH back. That would be R and S. And it would be 50-50, because you got a 50-50 chance of one side versus the other. But I'm telling you, you got S only. This means backside only. This means that the mechanism is SN2 for that reaction up there. Because SN1 was reasonable. It could have been SN1. But the stereochemistry tells us it was SN2. How is inversion obtained? Let's look at that a little closer. Here's the same compound. Same exact compound, but here I've got the bromine drawn in the plane. Still R. You can do that. How does the hydroxide attack? Well, if the bromine is going that way compared to the carbon, where does the hydroxide come in from? Comes in from over here, right? Right? Here's the bromine going that way on the board. So the hydroxide comes in from over here on the board. It comes in here between the methyl and the H. See, the methyl and the H is like this. Methyl going back, H is like this. The bromine's like that. These are a little down, and the other's here for tetrahedral. There it is on the board. This is H coming forward. Bromine that way. Well, the hydroxide comes in from over here between the methyl and the H. Kicks off the bromine, right? Backside. Let's look at the transition state. There's no carbocation intermediate, just a transition state. What does that look like? I'm going to have to raise this up. Well, maybe not, because I've only got this gap here. Don't need to raise it up. What does the transition state look like? I'm going to draw in this carbon. Transition state is where this bond is starting to be made. And we can draw that as sort of a half a bond. I'll just draw that condensed. Or the way I drew it, just put it a little closer so it's condensed. Or you can draw the bond in. Starting to be made. But this bond here, which is, that's sort of our mechanism, but what's the transition state as this is occurring? That's being made, what's happening to this bond? Being broken. But as it's being broken, it goes from a full bond to no bond. What's halfway in between full and no bond? Also sort of a half a bond. That's supposed to be straight. The alpha we're going to draw straight up. The H, these two groups are actually eclipsed at this point. The H is forward there, and the methyl this is our transition state. Sometimes you see like a double dagger up here or something. I'm going to put just the TS. Charge. Because everything over here adds up to minus. This has to add up to minus. You can't just create or delete charge. What's the charge of the oxygen? Here it's minus. Or just look up here. Over here it's minus. What does it become over here? What's halfway between minus and neutral? Partial minus. Not partial plus, partial minus. The bromine's neutral here. It becomes minus, Br minus. What is it here? Partial minus. And those two partial minuses add up to a net minus charge there. Does this seem like a transition state where this bond is being made, where the other bond is being broken? But at this point, it's almost equivalent. It's like partial bond because it's being partially formed. That's only a partial bond because it's being partially broken. What's the bond angles here between the H and methyl and these three groups over here? Bond angle between methyl and H. Bond angle between methyl and H. Thank you. It's a tetrahedral carbon with bond angles of 109.5. Okay. What are the bond angles right here between the methyl and the H? What's the geometry of this carbon here? These two groups are supposed to be drawn eclipsed. The ethyl is straight up, the H is forward, and the methyl is back. The ethyl is straight up, okay? If you're looking at my arm, this one is right in front of the back one. Okay? That H is supposed to be right in front of the methyl. Now, what type of geometry is this here? Trigonal planar. Yes. This goes to trigonal planar, and the bond angle here, okay, I'll draw here, or between any of these is 120 degrees. Or if you had this in full 3D, okay, the one I illustrated was the lower one, or you could look at this bond angle between the group up and the group forward, but that's 120 degrees right there. Okay? Now also, if this carbon became sp2 here, other than the hybrids, what does an sp2 carbon have? It also has a what? P orbital. And the p orbital would be perpendicular to that plane here. The plane here is like this. P orbital would be perpendicular . Now that center carbon looks like sp2 with the p orbital. The transition state, in the transition state, the carbon that's being attacked becomes sp2-like. In terms of its geometry, orbital kind of description, bond angles, okay? What are we looking at? How is inversion obtained, okay, right? Now, as this continues on, what eventually happens here? This bond completely breaks off, and this completely forms, right? Well, let's show the end result. We got it up there, but let's show it like this. Now, I reckon I'm not going to draw the carbon. I'll just have the carbon be a dot like that here. Now, if that's the carbon, where's the OH at? Well, it's over here. That's where it came in from, right? The ethyl group is now still straight in the plane, but it's kind of pushed this way. And this bond here, you can draw however you want. I'll draw it like that. There's the ethyl. The H is still forward. See, the H is always forward. It's forward here, but it's sort of back. It's forward here, but it's straight. Well, guess what? Over here it's forward, but it's pushed this way some. The methyl is always back, but it's sort of this way. We'll do this again, but let me go ahead and draw it. The methyl is pushed this. And there's your product. And indeed, that's R, but indeed, bet you steak dinner with a side of lobster that is S. And that's inversion. How did inversion take place? The nucleophile came in backside. But what did it do to all the groups? It's sort of like this, if I could do my hand this way. These groups are sort of, well, let's do a model. That may help better than this. Yeah. Alkyl straight up, bromine green, okay, that's actually an ethyl. Let's go ahead and just make it an ethyl since I got the bottles here with it and keep it clear. That's the ethyl group, bigger, yeah? Okay, straight up. As long as that bond's straight up, it doesn't matter how we draw the other one. I mean, that's straight up. That's the thing we're talking about. You can draw that however you want. Bromine green. Methyl's going to have to be blue and H is red. How does hydroxide come in? It comes in right here, backside to the green. Making bond, breaking, that's here. But when this comes in, it pushes these groups flat. Okay? These groups go all flat, all right? See, I'm trying to make that flat. I'm trying to make it planar. See that? That's what this group does. It pushes these flat. Then this gets kicked off. Leaving group. But now these groups, they move over there to replace that space. And I'm going to break my model now. They go that way. And now they're all going that way. It's like if I took my hand and it was like this. This came in, what happened to the hand? It flattened up, it became planar. But then when that group departed, all this went that way. And now my hand's inverted. Kind of like an umbrella. You ever seen an umbrella hanging like this? And then the wind gets it, and what does the umbrella do? It goes up like that. But there was a transition state. And between here and going up like that, you watch my arms go flat. Here's the transition state. Flat. Okay? But then it keeps going, and it curves up. But it goes through a planar flat transition state we call sp2-like. It looks like an sp2 if we consider that sort of a p orbital there. It's also called a 5-coordinate transition state because 5 things are bonded to the carbon. Bonded. They're not fully bonded. It's partially bonded. It's also a transition state. What else can we say about it? Transition states are often called activated complexes. You may see that term. Importantly, though, is bond angles is important. We go from 109.5 to 120 in the transition state. Yes. Back to 109.5, standard tetrahedral. This is the inversion. Okay, consequences of this. Reaction rates. I'm going to leave that up there. Let me move this above it. Look at these reaction rates for an SN2. Okay, and we're going to focus on SN2 for a little bit here. We're replacing bromine with I. Okay, that's I minus, right? Ionic, I minus, K plus. Let's forget about the K plus. I minus comes in and kicks off the BR. Nucleophile now bonded. If we balance this out, what will be over here? KBr, right? Potassium bromide. Difference in rate. If the rate up here is 1, the rate down here is much slower. Why is it much slower?
Well, let's look at the transition state for this mechanism.
Because the transition state energy, here we go. Here are two products. The transition state may be like this. That's the transition state energy, right? We call it activation energy. Isn't that the transition state up here? High energy. Okay. The transition state could be like that. And for some other reaction, which may start in the same way, which reaction is going to be faster? First one or the second? First one. It's all based on transition state energy. That's your activation energy. This is the rate determining step, right? Because there's only one step for the backside attack. Okay. Something is going on with the transition state. This is the problem. What's the bond angle right here? 60. What type of bond angle must be achieved in the transition state? 120. Question is really, which one can achieve 120 easier? The answer is the top one. This ring down here keeps it from achieving the transition state, the ideal transition state. Now apparently it can still happen because it does react. 120 is ideal. We know from Gen Chem that like 109.5 you looked at compression and you can't have difference. It doesn't have to be 120. This is just the ideal. Tetrahedrals don't have to be 109.5. That's just the stated sort of ideal. All right? The starting bond angle is way away from the ideal. And it's going to have to really stretch out. Can it stretch out? It's going to have a tough time doing it. That makes the reaction much slower. Yeah? We can keep considering this. That was bond angle up there. Down here, reaction rate. All of these substrates here, and the thing with the leaving group can be called the electrophile. This attacks the electrophile. That means, if you think about it, this thing likes to be attacked by electrons, because it's happening. If this thing likes electrons, we call this thing the electrophile. These things will be attacked by nucleophiles. We just call these electrophiles. The leaving group is on the electrophile. The electrophile has the leaving group. All four of these different electrophiles with leaving groups are very reactive. All four of these are much more reactive than just this. I've left this transition state up there. Why? It's because next door to where this is attacked, and this is attacked here, right? This is kicked off. This is what we're talking about. What is next door to the carbon that's being attacked? It's in the heading. It's actually two next door here, but only one of them is going to be relevant. P orbital next door. Why does that make the reaction easier? Well, let's put a p orbital next door in our transition state. Let's say there's a carbon bonded, and it has a p orbital. I think you can just add that in there. Okay. Carbon's back, p orbital, that H is forward. But what can we illustrate here? What can we show here? You got electrons in p orbital here, kind of. You got an electron here, and it's probably overlapping with something else, but what can we show here? P orbital interaction during the transition state. That is a stabilizing factor. It's going to lower the energy of the transition state, make the reaction easier. Yeah? Make sense? Heidi? Good? All of these are very reactive. They're also quite toxic because your body has lots of nucleophiles. Like DNA has amino groups that can react. That's how I think toxicity. Your eyes have proteins that have nucleophiles. If you get these chemicals in your eye, you're going to have a reaction is going to lead to irritation and stuff, okay? Right? Very reactive things tend to also be toxic. All those up there are toxic. This is much less reactive. And thus that one is not toxic. Not as, anything you don't want to consider anything just completely safe, but it is typically much safer. Relatively, okay? Those up there, most all those or all those, you're going to have big problems if you start breathing those or if they're spilled or released into the air or something, okay? Very reactive. Okay. Next, I think we can erase the transition state now. Next, effective carbon substitution. We seem to be focusing on the thing with the leaving group. I think that's what E says, right? We're looking at various electrophiles in the SN2. The electrophiles are things that contain the leaving group. Effective carbon substitution. Methyl bromide reacts faster than this propyl bromide. That reacts faster than, which is primary, that reacts faster than the secondary. And the tertiary is quite slow. Very slow. Pretty much doesn't react. Why? This is because of sterics, steric hindrance. If you draw this out, those H's are here, yeah? They're actually quite small, right? They may be even smaller than that. And the nucleophile can kind of get back in here, right? Now that's tetrahedral, it's actually coming between like that. Okay, there's room there. But imagine over here, and I'll just draw it in here, all these H's here. Right? And the nucleophile comes in here. It's like, hold on. Forget it. Okay? It's too crowded. It can't approach the carbon. This is called sterics. Sterics means crowding. Steric congestion. Steric hindrance. And you see, as you start putting, basically, you're looking at the carbon that's being attacked, because this one has what? There's two H's here, but then you also got this bigger alkyl group. And so it's worse than this. They get worse as you put more carbons on, because the carbons are bigger groups. Everybody see that? Steric hindrance negatively affects SN2. This reacts pretty darn quickly, easily. This is actually quite toxic. Methyl bromide is used as a fumigant. It's a gas. It's used as a fumigant on a large scale, and also where there's no humans around. They wouldn't spray it in your house where you might come in the next, after lunch. They spray it in like warehouses that have been abandoned, big places. They'll come in, seal it up, and just pump in methyl bromide and just leave it closed up for a week. And then you come back, all the rodents and roaches and everything is just dead. All right? Well, methyl bromide, you start breathing it, it's going to react with all your proteins and your DNA and the rodent, and it just leads to bad stuff. Okay? This is basically also toxicity. A little toxic. These get just less and less toxic. Relative. Okay? Because of reactivity. SN2. Here we go. Take home. Never do SN2 with a tertiary halide, this is called. With a halide on a tertiary carbon. Never. If you want to add another exclamation point, go for it. All right? It's too sterically hindered. And in fact, it will do other chemistry, which we'll talk about later. Now note, the above trend is just the opposite for SN1. But you already knew that. What's the rate determining step in SN1? Formation of carbocation. Which would make the best carbocation? Yes! The trend for SN1 is just the opposite. This will readily do in SN1, but this will not. And this will not. Secondary, possibly. We'll talk more about it. Okay? Here's some more reaction rates. Top here, displacing the bromine with iodide. Here they're using lithium. Acetone is the solvent. You can look at reaction rates. It should make sense based on what we just talked about. A trip to the dentist. Steric. So anybody looking to go to dental school. Dental anesthetics to numb the mouth or something. Lots of them. Novocaine, right? Procaine, lidocaine. You can look these up. They have different lengths of duration. Some of them are short acting. They'll numb the area for maybe 10 minutes. And then the effect will be gone. It's a quick acting anesthetic. Maybe you want to do a real quick procedure. You don't want the patient to be numb all afternoon if they only had to be numb for 10 minutes. But on the other hand, maybe you want to do a long procedure that takes 3 or 4 hours. Well, then you want a longer acting because you don't have to be giving the shot every 10 minutes. Okay? So, but if you look at these different anesthetics, they're very similar in structure, but they have sort of a difference, of course. And the difference is largely sterics. They become more congested around the amide group. These drugs are, the amide is hydrolyzed, and the length of duration depends on how fast the amide is hydrolyzed. If the amide is hydrolyzed fast, the drug only lasts a short time. If it takes a long time to hydrolyze the amide, the drug will last a long time. Well, the rate of hydrolysis of the amide is largely dependent on the sterics. And the ones that are highly crowded, highly sterically hindered, hydrolysis is slow, and thus the drug lasts a long time. You take a look if you're interested. That's an example of sterics influencing the reaction rate. But there's consequences of that. In that case, it's length of duration of the drug. Okay, so we focused on the group, the substrate with the leaving group. Well, actually, we're going to keep doing that. Different thing here. Leaving group ability. We said halogens are best, iodine is best, and bromine, and chlorine. Fluorine is way worse. Typically, F is not a good leaving group for these reactions. SN1 or SN2. Okay, a couple of reasons why. More stable anion. I- is going to be more stable. The length of this bond is also sort of a factor. The CI bond is longer. And so these electrons can sort of be influenced a little bit more because they're longer. And that's not easy to explain, but you may see length of the bond. Look at this example. If we take these two different substrates, reacted here, what's the nucleophile? Well, this is K plus, right? Okay, what's minus? What? Which atom is minus? oxygen, right? Okay. This is oxygen, CH3. That's a methyl. Got to be a minus to go with a plus, right? You got to know that. A long time ago, after a test, a student came up to me and said, "What is MEOC?" I said, it's this, just written backwards. Yeah? Okay. And I won't go further, but you got to know what is here, okay? It's pretty straightforward. You just have to think. It's organic chemistry. Let's get rid of spectator ions. This is O minus. Can this act as a nucleophile? These electrons come in, backside attack, kick this off. We just make the bond. Oxygen is now bonded to the carbon, right? Okay, SN2. All we have here is this different leaving group. Well, guess what? That reaction up there is very easy. This reaction down here is very difficult to impossible. What does that tell you about the F? Lousy leaving group. It's reluctant to do that. Okay? Much better leaving group. I'm just giving you some examples of this fact, okay? So there's your best. In general, bromine tends to be the most common because it's a good leaving group. It's better than chlorine. Then you say, well, why not just use iodine? Iodine compounds tend to be a little unstable. And iodine compounds tend to be more expensive because they're unstable and because iodine is just a little bit less common. Chlorine is the cheapest, but it's not the best. Bromine is sort of the compromise, and so bromine tends to be the most common. It's good and it's fairly cheap and the compounds are stable. Can other atoms be leaving groups? Can we make an oxygen a leaving group? Can an oxygen be a leaving group? Here's the start. A neutral oxygen is not a good leaving group for these reactions. It's actually worse than F. The question is really, can we make oxygen a better leaving group? And we can. There's a couple of ways. First way is by protonating it. First off, if this was an oxygen like an OH, and you come in here and try to do that reaction and replace it with the OMe, there's going to be no reaction. Nothing. Okay? Hydroxide will not act as a leaving group in a slow rate determinant step. We can do some chemistry here, though, if we include acid. Okay? Strong acid. This would be called a strong acid. What we're looking at. Now, often it's a catalyst, but it may not actually always be a catalyst. It all depends on what, if it's regenerated at the end, right? So, I don't want to say catalyst because while it often is, it may not be a catalyst. In fact, in the reaction we're doing right here, it's actually not a catalyst. Mechanism here. We protonate the oxygen. It's almost like an acid-base reaction. These electrons attack the H+, which could come from maybe sulfuric acid or something. What does that give? The oxygen is now bonded to an H, with a lone pair left, positive charge, right? Standard acid-base reaction. Is this a good base, though? talk about this. Is this a good base? What did we say about bases? It's neutral. It's a neutral oxygen. What did we say about neutral atoms being bases? What are good bases? We said this before. Bases are anions, minuses. Hydroxide is a good base. It's not O minus. This is O, neutral O. And we said, really, the only atom that is a good base when it's neutral is what? Nitrogen. A neutral oxygen is not a good base. So why am I showing it acting as a base?
Because it can.
What?
It can act as a base.
It can, it's just not a good base. It's all relative. You gotta have a strong acid for it to act as a base. And this equilibrium is really quite bad. Okay, this is not a good equilibrium we're showing here. I'm not going to give you pKa's because they're both very odd, but it's bad equilibrium. That doesn't mean it's not some. Maybe 1 out of every billion is protonated. But that's what we're doing here. It's a bad equilibrium. But this structure here, now the oxygen's a better leaving group. Now the nucleophile, in this case it's methanol. These electrons will come in here and kick that off. And I now see that we can answer the catalyst question. We'll get there. I was kind of wrong. What is this? What does that air movement give? Boom, boom, boom. What's now bonded to the carbon? Oxygen. All right. Let's draw all these bonds out in the methyl group. What else is on the oxygen? H. How many lone pairs on the oxygen? 1. And charge? Positive. There we go. Plus what? What did we create here other than this? Plus water, right? There's the water we said we would form. Well, how do we get to final product? What do we need to do? There's got to be a minus here. What acid did we use? Okay, let's say we used H2SO4 and we have bisulfate anion here, minus. This can take the H, these electrons stay behind. What does that give? That gives the product, but what do we reform? Yes. So in this reaction, was the acid a catalyst? Yes. It was a catalyst in this reaction. We reformed it. What did the catalyst do? It made the oxygen a better leaving group. How? By protonating it. Protonating it, the oxygen became positive. Now it really wants its electrons back. It can get them back by taking these and basically leaving. When the oxygen leaves, it left as neutral water, a neutral oxygen. Up here, it would have had to leave as what? Hydroxide. And what did we say about hydroxide? Okay. Okay? But neutral water will leave. And we can get it to become neutral water by protonating it, and when it leaves, it's leaving as neutral water instead of a minus. So that H being there allows us to leave as a neutral oxygen. Okay? Very common way to make oxygen a better leaving group. A typical issue here, and some of you did it on the test mechanism, particularly the second mechanism. You got to be careful removing H's. Some of you guys will do this here, but when you do it, you will first remove the H and you will make MEO minus. Or you'll just consider that ionic. That's not ionic. Okay? Did I do anything to the methanol before I use it as a nucleophile? No. But when you guys do it on quizzes and tests, you do all types of stuff with the methanol first. The nucleophile does not have to be minus. All it has is a lone pair. And you're not going to make it minus. You're under acidic conditions. Making that minus is like making hydroxide under acidic conditions. You don't make hydroxide under acidic conditions. Okay? So, you got to pay attention to these details and not do wrong things. The good news is, the more experience you get, you do things right and you stop doing the wrong thing. Right? Keep these things in mind. There's details here. Okay. What's the problem with this reaction? What if we try to take this? Will this reaction work? I can protonate the oxygen with the acid, and then I can use this as nucleophile, and the OME can come in and kick off the water. Why would that not work? Well, because you can't have a strong base and acid in the same reaction. You can't have your cake and eat it too. That's acid. That's a strong base. That's just like KOH. The difference between the H and the methyl is nothing. It's hydroxide or methoxide. They're both the same strong base. You can't have strong base and acid in the same reaction. They'll react with each other. Like when you combine hot and cold water, they react and it becomes just lukewarm. A reaction that can work here is very common. Analogous is to react an alcohol with something like HX, HI, HBr, and we can get an alkyl halide. Now this we can consider H plus and I minus. But you can have I minus with acid. That's the definition of a strong acid. But you can't have O minus. Because an alcohol is not a strong acid. And this is a very common reaction of alcohols. And so show that mechanism. Show the mechanism of this reaction. Just leave it right here in this space. Show the mechanism of that reaction. And we'll take a 2-minute break at the same time. can also maybe show the product of the next reaction down here with the HBr.
Okay, we've got H plus because we have a strong acid with HI. We can just show it ionized. We can protonate the alcohol. Boom, boom, boom. Now, when you do a mechanism, you don't have to consider equilibrium here. But again, this could be a poor equilibrium. You could argue that, but okay, poor equilibrium, we mentioned that. But I want to make one more point about that. What's the next step? It's only one more step, right? What's next? You got I minus, which is also there. You see HI supplies both the H plus and the I minus and the nucleophile, and so these electrons come in here and kick off the, yeah? And what does that arrow movement give? You're done. That gives products, right? By what mechanism? SN2, yeah? A couple of questions here. How many intermediates in this mechanism? One, you see it? It's a protonated oxygen species. Yeah. Yeah? But I thought SN2 did not have an intermediate. Isn't that right? Does SN2 have an intermediate? It was just a transition state. But there's an intermediate here. Yeah, there's an intermediate here, because the intermediate came before we did any substitution. This is the substitution right here. And do you see any intermediate between here and the product? No. The first step is not part of the substitution. First step we call activation of the leaving group. Okay? But I always get the question, I thought SN2 there's no intermediate. Well, there's not. All we're doing here is making the leaving group better. That is an intermediate in the overall reaction. This reaction consists of first making the leaving group better and then doing the substitution. And when you do the substitution, there is no intermediate. So just keep that in mind here. Because did we make a carbocation here when we did the substitution? No, that's the intermediate that we did not make here. There we go, SN2, substitution. This is what I want to say here. This is a bad equilibrium. So maybe at equilibrium you got 100 of these and only one of these. Well, guess what? When this reacts, it's gone. What happens to this equilibrium? When this thing here reacts, it's gone. It's no longer there. Thus, what happens to this equilibrium? It shifts which way? To the left. To what? To replace what's gone. That's how it shifts. That's what Le Chatelet taught us, right? Okay? So when this reacts, what happens up here? More of this is formed. And then it reacts. What happens up here? More of this is formed. And before you know it, all of that is gone. It's all over there. So you're working through a bad equilibrium, but as it reacts to the equilibrium, even though it's bad at any good point, it adjusts. And that's how you go through and you end up at the end. Understand that point? Okay? Because if you remove something from the equilibrium, it will adjust to replace it. So more of this is formed, then it reacts, more formed, it reacts. So even though that's bad, it's okay. We pull it through. Question, is the H plus a catalyst in this reaction?
No.
Is it a true catalyst?
No.
Was it reformed? No. So what, you don't call it an H plus catalyst here, you call it maybe a promoter or something. You don't use the term catalyst. Because it doesn't fit the definition of a catalyst, right? See that? There's no acid over there. The acid is consumed here. Did we get a product down here? Now in my examples we're using OH here. We're making OH a better leaving group. But really focus on the oxygen. It doesn't matter that that H is there originally. Focus on the oxygen and just the same chemistry. That is, can we do any chemistry here? Do we have a leaving group? We have no halide. What's next? Oxygen? How do you make oxygen a better leaving group? Protonate it. Can I just protonate it without having to do the mechanistic step? Now, in a quiz or a test, you've got to show mechanism for that. But can I just protonate it? Everybody good? Okay. So we assume we can protonate it. Now what? Somebody have product? Somebody have product? No. Nope. Somebody else have product? No. No. Anybody got product? Nope. Whoa.
That's all obviously.
Nope. Why did you do that? At this point, the Br minus, which is here, does what? Attacks that, kicks that off. What do we get? We get that plus what? Bromine is now bonded to the ethyl, right? 2 carbons bromine, and kick that off. What's so wrong with that? Same thing we did. Oh. Why not? We take carbon kick off leaving group, right? How did you get your product? You attack this carbon. Well, you said a word. That word is not exactly correct, but if we're going to go with that word, what do we say about that? Now, we added an extra exclamation point. What do we say about that? You called it a tertiary carbon.
Yeah.
And we said over here, you never do SN2 with a tertiary.
Yeah.
Now, halide can be a general term. That applies to any leaving group, okay? We can have other, that's any leaving group, okay? But that's not really the answer, because really that you wouldn't call that a tertiary carbon. Because usually primary, secondary, tertiary applies to sp3 carbons. Here's the main thing. I'll refer you back to the first page, other than the warm-up page. And what's the heading of this? What's the title of this handout? Nucleophile substitution at what type of carbon? At a tetrahedral carbon. Yes. Yes. Okay. Now that we've reread the handout. And there we go right there. We had a choice. See, up here you did not have a choice. There was only one carbon. We attacked it, kicked off the water. We didn't have to talk about it or think about it. Here you have a choice. The oxygen can leave that carbon or it can leave that carbon. Which one are you going to attack? The tetrahedral carbon. Over there, kick it off. That's not a tetrahedral carbon. That's a trigonal planar carbon. You don't do SN1 or SN2 at trigonal planar carbon. You do it only at tetrahedral. Okay? Many reasons why. Here's one reason. If we attack this carbon, the weaker bond will break. Which is the weaker bond? The bond to the leaving group or the pi bond over here? The pi bond over there will break. And at that point, you ain't doing SN1 or SN2. You had a choice. We attacked the tetrahedral carbon. Knowing that, is that the products? The text here. So what was the whole thing here? This was, in fact, what in the reaction? That was the leaving group. That's more than water. That's a substantial organic product. But it did serve, that was the leaving group in the reaction. Everybody agree? Isn't that what left this carbon? Yes. That's a substantial molecule, though. Yeah.
Could it do resonance and still be?
Could what do resonance?
Could the oxygen zone pair be resonant?
Right here? What would resonance do for you?
I don't know, I was just wondering if it would do anything or if it would just go along with that reaction.
It's interesting. Can a positive oxygen do resonance? It's going to be reluctant to. Resonance involves delocalizing this lone pair. If you delocalize it, the oxygen is going to lose electron density. Do you think that oxygen is going to be willing to lose electron density? Positively charged. So while you may theoretically be able to show it, you have to understand that that oxygen is not going to want to share its electrons by resonance. It's positively charged. So it's a gray area, and I would just, you got to think. If you start moving to resonance and putting over here, that's going to become 2 minus. Oxygen really ain't going to, I mean not 2 minus, 2 plus. It really ain't going to like that. Okay. We're broadening this out, okay? You can't just memorize certain reactions. You've got to be able to assess and predict, okay? The details here, yeah? Remember, I think remember is tetrahedral carbon. Right? Very good? Now you can check the tape. When we first started this reaction, I said, we're going to attack the tetrahedral carbon. I said that a couple of times, but then I stopped saying it. I knew this was coming. Reinforced. Tetrahedral, right? Okay. What's another way to make oxygen a better leaving group? We can convert an OH to a tosylate. What is a tosylate? This here. So OH, the oxygen we bonded to this sulfone, a sulfone, sulfur with 2 S double bond O, 2 of them, sulfone. I reckon it's sort of like a ketone, but it's 2 oxygens. Benzene ring methyl. Benzene with a methyl is called toluene. It's a solvent. We may be using it this week in lab, yeah? Toluene? I think we may be using it today. Can't remember. Possibly. You can buy it at Lowe's in the paint section. It's used as a paint thinner or something. Toluene, sulfonyl. Toluene, sulfonyl, and the oxygen would be a kind of like an 8, like a sulfate, phosphate. Toluene sulfonylate. Well, that long word has been shortened into tosylate. Toluene sulfonylate. Okay. Shortened to tosylate. That's where tosylate comes from. It's the entire group here. Now, there's variations of this called mesylate. Mesylate is where it's just the methyl coming off, so it's methyl sulfonylate. Methyl sulfonylate. See it? You can also have triflate, which is a trifluoromethyl sulfonylate. There's no M there. It's just called triflate. These are more advanced. Okay. Triflate is most common at the introductory level. One of my handouts, they do use a mesylate instead of a triflate. Okay. It's the same idea. I just kind of show you a couple of others. Tosylate's the most common. At the intro stage, triflate's kind of the best, and it's used at the sort of upper level, more advanced chemistry. Okay. How do you make tosylates? You make them from tosyl chloride. Tos. Now this is O-tos, because the oxygen is there. Tos would just be toluene sulfonyl. And by the way, I always say TOS. So I can say O-tos. Strictly, it's just O-TS. So in your textbook, it's not just going to say just TS. All right? But I say TOS. Tosyl chloride is just where the tosyl is bonded to a Cl instead. So it's Cl here. I'm just going to denote that there. You need to know the structure of the tosylate. Okay? That's sort of like Greek phi. That can be used as a generic for some type of aromatic ring. Okay? And it has a methyl substituent. That's just a shorthand, so I don't have to draw that out, waste ink, and then have to erase it. Okay? But you do need to know the full structure. But if we're going to draw this 100 times, we can just do a little shorthand. Tosyl chloride. Pyridine. Have we seen pyridine before? Pyridine is benzene with one nitrogen instead of carbon. And the lone pair is in an sp2. It's slightly basic. It's basic enough to act as a base. It's a weak base. I'm not going to do mechanism here. I do mechanism for this in organic 2. It's got a pi bond here. It's a little bit different. It is a substitution reaction. Here's your product. Tos chloride is here. In the product, the oxygen in the stuff has just replaced the chlorine. Okay? You can keep this here. I'm going to just do this. We replace the chlorine with the oxygen. And the oxygen has the alkyl group. It's also got some stereochemistry, I see. We can draw it the other way, but boom, boom. You see how the oxygen has replaced the chlorine? Well, we also lose an H to go neutral. If you balance this out, we're going to form HCl. Pyridine is there to react with the HCl. So a lot of times you don't want to generate strong acid in a reaction. You include pyridine to react with the HCl to have everything be more towards neutral pH. Okay, so this is just a substitution reaction, And that's how you get the oxygen bond to the tosylate group. You can actually isolate this. Okay? It's isolable. That's short for isolatable. Okay? That's a term, that's a word. These can be made, purified. Okay? Now, the OTOS is a good leaving group. And now we can come in with some type of nucleophile. Take that off. And of course, if we have stereochemistry here, if that's forward, how does a nucleophile come in? It'll come in back, right? Importantly, in stereochemistry, if this was whatever, forward, it's still going to be forward here. There's no change in stereochemistry here. Because when you make the tosylate, do you do any chemistry at the carbon? No. So that remains forward. But now we're doing chemistry at the tetrahedrocarbon, backside attack. And that's how you get inversion. So tosylates are good leaving groups. You do not have to have strong acid to make tosylate a better leaving group. This is another way to make OH a better leaving group. Here you're converting it to something else, which can actually be isolated. Back up here, when we protonate the oxygen, you don't isolate the protonated oxygen. That is just an intermediate in a mechanism. But you can actually isolate the tosylate. Okay. Can a nitrogen be a leaving group? Actually can. But only if you can give it a positive charge. Now, many books will not discuss nitrogen as leaving group because it's not that common. Oxygen, very common, the way we discussed it. But nitrogen can be a leaving group too. If you take this dimethylaniline and heat it with HI, we can actually remove a methyl group. Tertiary amine. Correct? Everybody agree? Tertiary aniline. What do we have here? Secondary aniline. We've removed a methyl, which is an alkyl group. Can we use that term? Have we done a dealkylation reaction? Yeah, we removed an alkyl group. Everybody good with the terminology? We can dealkylate this tertiary aniline with HI and get the secondary aniline. More specifically, we can say we can demethylate it. Okay, mechanism. Now we're also going to form up over there. Mechanism. What's going on here? What do you want to do first? General point. This is strong acid, right? Usually when you have strong acid, the first step in your mechanism is to protonate something. Otherwise, you probably wouldn't be using strong acid. What do you want to protonate? Well, let's protonate the nitrogen. What does that give? Can I just show the ring as phenyl? It might be best to draw these methyls out as CH3 groups. Protonate the nitrogen. What do you want to do next? Hopefully you can see this. the next step is the nucleophile attacks the tetrahedral carbon and kick off the leaving group. Can a positive nitrogen be a leaving group? Yes, that's what we said. And what does that give? Here's your SN2. Did everybody see this before we started? Now in this case, the methyl got substituted. There's the methyl. It used to have a nitrogen bonded to it, but now it's got an iodine bonded to it. But in this case, maybe this is your major product. Sometimes the leaving group is a major product. Everybody see this chemistry? Yeah.
Why did it decide, like I understand the mechanism, but like when we did it like above, we'd have, usually it was like the iodine would attach to it. So like why did the iodine decide to attack the tetrahedral carbon and not the nitrogen? Because isn't the nitrogen also tetrahedral?
We kind of showed that previously at one point. You want to attack this?
Yeah, I was just wondering.
Probably mainly because you want a minus to attack a plus. Okay. Well, what would you get from that? You're going to have a nitrogen with this. Are you saying that would be? Are you proposing that as a product in your question?
And then like,
Why are there two items?
Go ahead.
sorry,
You wrote two items.
because of that
Item-
Yeah, I guess like something would have to leave without.
This here?
Yeah. And like that would make sense, so never mind, that makes sense, that why I would attack carbon.
I can't hear you. What do you?
I said like that, but yeah, it makes sense now why I'd attack the carbon, because obviously that structure wouldn't make any sense.
Okay, why does this structure not make any sense?
Because like, well actually, I guess
It's
neutral.
neutral.
It would be neutral, so yeah,
Well, it is neutral, but I agree with you that that structure doesn't make any sense, because that's a very odd nitrogen. It is not a standard nitrogen. Standard nitrogen is 3 bonds, 1 lone pair. Oh, I'm sorry, here's the reason why.
It has 5 bonds.
It has 5 bonds around it. It has 10 electrons around it. Nitrogen only has 4 orbitals. It can only have 8 electrons around it. So that's a major golden rule. So are you still thinking that that must be?
no, that makes sense.
Okay. So yeah, the transition state leading to this product is going to be so high, I have to go to the Empire State Building. Okay. It's going to be, okay. This is the chemistry that's going to play. It's leaving group chemistry. We got a tetrahedral carbon with something that's only they can leave. Nucleophile comes in and kicks that leaving group off. What type of products do we get from that reaction? We get a nice looking standard nitrogen, 3 bonds, 1 lone pair, and we got it. It's a reasonable question, basically because you want the minus to bond to the plus. But you see what that gives? It gives insanity. So that just doesn't happen. Good question. Okay. We got another way for things to go neutral. Okay. The nitrogen gets its electrons from taking this here. Okay. That's actually a name. You don't need to know this name. Now, some names you need to know. This one you'll never hardly see. It is called a Herzig-Meyer reaction, but you ask most chemists are going to be like, what? Never heard of that. I'm just showing it to you because it illustrates nitrogen being a leaving group. Can be. It should make sense. It's leaving. It leaves as a neutral. Okay. These guys used to sell furniture on Whitesboro Road. Remember that there? Herzig-Meyer? What was it? What was it?
No, I think it's Perlingmeyer. Yeah, they used to sell furniture up there on Washington Road. I think Riceboro Road. No, that was Perlingmeyer. Okay, can sulfur be a leaving group? Okay, we're going to look at every atom on the periodic table. Eventually we'll make it over here to niobium or zirconium or something. Okay. How about sulfur? Can it be a leaving group? Actually, yes. But as an oxygen of nitrogen, it typically must be made positive first. Sulfur is used a good bit for your body, in your body, by your body, biochemistry. Norepinephrine, in the synthesis of norepinephrine in your body, this nitrogen here can act as a nucleophile. It attacks this methyl group, which is on this positive sulfur, and the sulfur gets kicked off of the tetrahedral carbon. There's multiple steps here. The nitrogen then has to lose an H to go neutral. Something can take the H. Now we've methylated the amine, and that's called epinephrine. What are other names for these? Yes, this is adrenaline. Okay? It's be called noradrenaline. This is how your body. This is sort of a cofactor type enzyme or something, but it has a positive sulfur on a tetrahedral carbon and it gets kicked off. Okay? It's doing SN2. This thing is the electrophile. This is our good old SN2 chemistry. That's how your body makes adrenaline. Nor. What does nor mean? Nor, typically when you see that prefix, it means it's missing something. Okay? What is that missing compared to this? Missing the methyl group. And so it's called noradrenaline or norepinephrine. That's usually the case where maybe this molecule was sort of identified first, and then later they identified one that was missing the methyl, and they used the nor terminology. Okay? You can actually buy, it's called SAM, S-adenosine, you can, I'm not quite sure, but you can actually buy that at the drugstore or whatever in the supplement aisle. So if you think you need more methylation going on in your body, you can, okay. So that's an example of sulfur being the leaving group. Positive though. Application, sulfur and nitrogen leaving groups. Mustard gases. You ever heard of mustard gas? Where was it used? Mustard gas was used in World War I as a war gas back when the chemistry was first starting to get going. They just, well, we can kill people with this. Yeah, okay. Now it's sort of outlawed, the rules of war. The simple molecule here will kill you if you inhale it, okay? It will not be nice. What's going on here? Why is it so reactive? Okay? Well, you could envision just kicking off one of these chlorines here. Nucleophile coming in here. Yeah, and kicking that off. So there's actually some electrons that are closer. What electrons are closer? And these electrons come over here and kick that off. And that leads to what? Well, what does that arrow movement mean? This sulfur is now bonded here, right? And what's the charge of the sulfur now? Positive. And this readily happens. But now what do you have? Now the nucleophile, it may be a minus, it doesn't have to be a minus. These electrons now attack this carbon, tetrahedral carbon, and kick that sulfur back off. But this is highly reactive. Why? I mean, you got a leaving group, but what else makes this highly reactive? ring strength. This really wants to be opened back up. This is begging for some nucleophile to come in here and kick that sulfur back off. Okay? So this is a sort of a reactive intermediate that's formed from these things. Sometimes this may be called a neighboring group effect. The sulfur there leads to this, and this is highly reactive. You also have some cancer drugs that are like this, nitrogen mustards, and you have the same thing here. These electrons coming here, and you get a three-membered nitrogen ring that's positive. Okay? Basically, these are potent alkylating reagents. Have we looked at alkylating? What does alkylating mean? We're adding a, yeah, that's what we did up here. We alkylated this nitrogen. We added enough. Whenever you do substitution, you're typically adding an alkyl group because you're attacking a carbon. I mean, this nucleophile is going to be bonded to a carbon. Carbon typically called an alkyl group. It's a tetrahedral carbon. It's going to be called an alkyl group. So this is sort of an application. It forms these three-membered rings, which are highly reactive. Not only does this carbon have a positive leaving group, positive sulfur, also a ring strength. It's like I'm stuck like this, okay? And I'm like, somebody please come help me out here. Ooh, nucleophile. The nucleophile is just attack, attack, attack. And that's your DNA attacking or something. Okay, your proteins in your lungs, I mean, everything.
And then it creates
Where do you see that
it's
at?
at the end. Because it
Oh.
takes away one of the H's from the NH.
Okay, why didn't you tell me it was already drawn down? Yeah, because if the nucleophile has an H, it's going to want to go neutral afterwards. That can take the H and create ACL. You got double problems. Now you got ACL in your lungs. The more you breathe in, the more ACL you create. Because this chemistry is very fast. Okay. Before we saw some substrates that reacted because they had a p orbital next door. These are reactive because they make this, remember, the ring real easily. Now we're going to look at the nucleophile. Okay? We looked a good bit at the thing with the leaving group. Now about the nucleophile. Anions are more nucleophilic than neutral counterpart. For example, hydroxide is more nucleophilic than water. Oxygen anion versus neutral oxygen. Better nucleophile. Same thing with nitrogen. Better nucleophile. All right? Anion more nucleophilic. The question is basically, I mean, if we have something like this, which one of these is going to be more attractive to this carbon? By the way, did we even mention why it would be attractive to this carbon? The carbon's not a plus, is it? It's not a formal plus. What does it have? It's partial plus. Which one's going to be more attractive to it?
The negative one.
The anion, right? These electrons can come in here and we can get this chemistry to take place. We call that SN2. We can get this substitution reaction to take place. Okay? Next, a less electronegative atom has the more nucleophilic lone pair. We've sort of have said this before when we talked about acid-base chemistry. Ammonia is a better nucleophile than water. Why? Well, oxygen they're both neutral, so you can't look at minus versus neutral. They're both neutral here.
But what do we know about oxygen? How does it hold its lone pair? Tighter. And so it's going to be less prone to going and attacking this. Nitrogen, lone pair down here. Okay? It lets its electrons get in here and do backside attack. Easier. Okay? Electrons more available to react, yeah? That's analogous to the same in looking at those bases. By the way, what's the difference between a base and a nucleophile? Not much, other than if it attacks an H, we call it a base. If it attacks anything else, we call it a nucleophile. See, here it's attacking a carbon. So instead of calling it a base, we call this a nucleophile. Yeah? Now, there are some slight different considerations we want to consider. So that was an example of the same row. Straight across, up or down, which is a better nucleophile, H2S or H2O? O is a better parent. With H2S, the electrons are more out there. Sulfur is not as electronegative. Sulfur is also bigger, which puts the electrons out there a little bit further. And the more the electrons are out there, the more they can be kind of perturbed a little bit and moved. Which is better nucleophile, I minus or F minus? Typically want to show lone pairs when we have charges. I minus. Because F minus holds the electrons tighter. Better parent, right? Also smaller. Because it's smaller, it's just so, it's called harder. See, the F can be here and it can be so tight, it's like, okay, yeah, I got to get real. But the I, the electrons can do a little bit more. Wow, the reaction just happened. Okay. The more the electrons are out there, the more they can be perturbed and moved and directed and stuff. That's another kind of reason. I minus is actually a pretty good nucleophile. F minus is pretty lousy. Note that I minus is thus both the best nucleophile and the best leaving group of the halogens. Steric effects. We'll have a quiz in the morning. What have we got so far? We've got resonance, chemistry of dienes. Yeah? Need to have a quiz tomorrow morning. Maybe we should see if there's any questions about dienes. Any questions on dienes? Questions on dienes? How do we do on this page here? Can we do this one for us? Everybody got a product for this one? We got something, Mike? Everybody got a product? Well, the answer's in the back. I mean, have you done it? Got something? Was your answer right? I'll have to, where's it? I'll have to, see here, okay, tertiary, secondary, okay.
Did you look at the answer? So you already knew it, right?
Yeah.
Okay. But you did it on your own?
Yeah.
Okay. Do you have any questions about it?
First thing we need to decide is which alkene is ultimately going to react first. We need to do this by reacting them both or considering. I can do it in my mind because I can see. Whenever these react, you're always going to make an allylic cation. Where are we going to make cation at? Left or right if we react here? On the right. Why? Because it would be resonance stabilized. So we react on the right, so we pull that away. On the test, many of you have arrows that are just not right. Arrows show movement of electrons, not atoms. And even if you are thinking you're moving electrons, if your arrow originates from an atom, your arrow is incorrect. And WDAM stands for what? What does arrow mean? I'm saying I don't know what your arrow means. It's either because it's just drawn wrong, backwards from an atom instead of electrons, or in some cases your arrow can be perfectly correct, but then you draw a resulting product that's like, that did not come from the arrow movement. So then I have to go back and say, do you really know what your arrow means? So I'm like, what does arrow really mean? You got to have a correct arrow, and then you draw what that arrow leads to. So there could be many reasons why there was a WDAM. Of course, you can ask, because they're all very different things. But the arrow is very important. That's going to give boom, 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 boom. The new H is added to which carbon, left or right? The left carbon, correct? These electrons are being pulled away from that other carbon. Going to attack. They're bonded here. Here. I'm going to show the H down because I don't have room to draw it up there. And I'm not really showing any precise stereochemistry here.
Missing a
That's not, I'm missing something here.
map. Map on the double one.
Okay, here. Positive is here, right? Now we can do resonance. Windshield wiper over. Double-headed resonance arrow. This is going to give boom, 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 double-headed resonance arrow. No, I mean double bond. New H here. Where's the plus now? There. There you go. There's our resonance stabilized allylic cation from that attack. Primary and secondary. Is that right? The true structure is a blend of, okay, it's got characteristics of both, just like a pink has characteristics of both red and white. But what if we reacted over here? Where are we going to make cation at? Right, left or right? Left. And that would give boom, 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 boom. New H on the end, positive here, double bond here. Allylic cation, now we can do resonance. Yes, there's a new H on the end. Positive here, is this looking right? What do we have over here? This is one thing. Neither structure is correct. The true structure is a blend. The blend has characteristics of tertiary and secondary. Which blend is better? This one, right? Forget about it. Okay, where does the I minus attack? If it attacked there, we get iodine here. Attack there, there. Which product are we going to get? We're heating. Which product do you get with heat? With heat, the answer is most stable. In the original example, it was 1,4, but it doesn't always have to be 1,4. With heat, you get the most stable. Which would be the most stable? Iodine. Well, we look at the double bond for stability. There it's disubstituted. Here it is trisubstituted. The iodine attack's here. I mean, I'm not going to show full mechanism, but doesn't the iodine attack either here or here? If you show iodine there, it's a disubstitute alkene. That is here's your product with heat. Is that a 1,2 or 1,4 product? Yeah, the new H is here. It is a 1,4. It is. I'm telling you, the 1,4 is not always the most stable. You have to look at them. Okay, we're out of time there. I'm going to do what?
Lab reports.
Lab report what? Oh, bromination lab report? Oh, you didn't turn them in yesterday?
No, there's.
Other half is turned in today? Okay. Group lab report due Monday for both sections. Okay, on your way out, please turn in your bromination lab report.